So we're given this the response, step response, and to get the transfer function, we need to measure the y1, which is over here, y1 and y2, and this is just literal amplitude or length of. And once we have them, we can figure out the transfer function. So first, what order is this? Is the first question we should ask, and we can tell this is second order filter. And if it was a first order, it's gonna and if it was first order, it's gonna look something like that. And we know for second order system, we have transfer function of something like, so second order s squared plus 2 plus s plus wn squared, and this is the order for second order. And we have to figure out the ratio between them, between the y1 and y2. So y1, y2, we have to put natural log. And if let's say y1 was 2.3 and y2 was 0.3, then we should have ln of 2.3 over 0.3, which should give us 2.04. Now, now that we have this, we can calculate the damping coefficient, which is that over square root of 4 pi squared plus that thing squared. And notice that this is just only pi squared, not 4 pi. It's not the whole 4 pi squared. It's just the pi itself. Or we can think of it as 2 pi or 2 pi is squared. But either way, it should give us the same result. 4 pi squared plus 2.04 squared should give us 0.308, and that is our damping coefficient. And we know that this is underdamped because it's less than 1. Now we can get, so we know this damping coefficient, but we still don't know a damping coefficient, but we still don't know Wn, the natural frequency, I think. So Wn equal 2 pi over t, which is the period. So 1 minus damping coefficient, 1/2 over. And this t is the distance between this t1 and t2. So this is the period. And this thing is called t. So this is the period. And let's say the t is 0.065 second. Let's just say that. Then we should get 2 pi over 0.065, 1 minus 0.308, which we got it from here, 1/2. And if we calculate this, we should get Wn equal 116 radian per second. And if you put these numbers into this transfer function for second order system, we should get transfer function of 13503 over s squared plus 71.4 s plus 13503. In the second part of the question, would it be appropriate to record the arterial blood pressure? Well, we need to know the frequency content that it can measure. And how we get it is now that we have this Wn, we can just simply calculate it, convert it into the frequency, to hertz. So 116 times 180 over pi, I think. No. So how you're supposed to get it, I think, is, so the frequency, damped frequency is 1 over t, which we have 0.065 over here. So 1 over 0.065, and you're supposed to have 15.4 hertz. And the natural frequency is defined as Fd over 1 minus damping coefficient squared. So if you do that, you should get 16.2 hertz. And if you look at the table 1.1, the arterial blood pressure frequency goes up to 50 hertz. So because our natural frequency is less than the frequency of the blood pressure, it is not appropriate to measure a blood pressure.